So I would like to invite Dr. Sikarin Yoo-Kong. He will present all of you in the title of the integrable system. Dr. Sikarin, please.
Okay. Hope you can hear my voice. Okay, everyone.
Yes.
All right. Good. So, well, I would like to introduce myself again. My name is Sikarin Yoo-Kong, and today I'm going to give you like a very gentle introduction to the integrable system. Let me share your screen. Can you guys see my screen now?
Okay.
Okay, good. So, well, so here is well, let me start right away. So when we talk about integrable system, this subject is very huge. So I would like to make it to be 4 parts. You can say this is the quantum, and then this is maybe classical, and then this is continuous, and this is a discrete. Okay, but today what I'm going to tell you guys is something on this bit here, a tiny bit here, because as I mentioned, this subject is very huge. So we're going to focus only for the finite dimensional system only, or well, or more specifically, this is the Hamiltonian system that we are going to talk about today. So hope you guys can read my handwriting. Okay, so the first question, what is integrability? That is a good question to ask first, right? So the answer is, the answer can be varies from subject to subject. What I mean here is that there are many notions of integrability. Well, because the field is very huge, right? But well, what I'm going to tell you today is something to do with the Hamiltonian system. All right, but intuitively, I can give you some simple idea. The simplest motivation, okay, can be viewed from the first ODE, right? Suppose we have this differential equation, first order. If you want to solve for y, then you need to do the integration. Of course, that is the thing. Here is the point. If the integration can be done, right, explicitly, right, of course you're going to get the solution, which is actually y, right, by means of the quadrature. Okay, Well, what I mean by this quadrature is mean that it's something to do with the process that you use to compute the area under the curve, the determining the area of a plane geometry, something like very basic stuff. Well, I think everyone learned this from like first year calculus, right? So if you, well, you give the boundaries. So if you want to computing, this is the area under the curve, which is actually you need to do the integration. All right. That is the very intuitive or very simplest, simplest example that we can have, right? Okay, but well, in physics, right, we normally deal with not only the first order, but we deal with the second order ordinary differential equations such that, like this double dot, well, this is the Newton equation in case of 1D, right? So this means that we have to do integration 2 times. Okay, all right. But the thing is that, however, well, there is always to reduce a number of integration if your system possesses a constant. If, like in this situation, the energy of the system is conserved. Okay, so if it's conserved, then you can write E is the sum of the kinetic energy with the potential energy, right here. And then you can convert this into this relation. And you could see now you get the first order equation out of it instead of this one. You don't need to look at this second order. Now you get the first order. And then once you get this, you could say that, oh, okay, you can do the integration and then you do the inverse relation somehow, and then you could get this expression. Okay. Okay. But the thing is that, here is the thing. So the explicit solution can be obtained if one, the integration can be done is okay. If you can do the integration explicitly, of course you're going to get the solution. This is the first step. The second step, one can perform the inverse relation right? Something like here, and then you could get x as a function of t at the end here. All right. If you could do this, you can say that your system is integrable. It means that you can do the integration explicitly in that sense. All right. Hope you get the point. All right. So here I would like to put a remark. Yeah. So, well, if we look at this page carefully, what I just did here is that, so because the energy is the concept one, right? Then we can do this kind of whole process. And then and again, if you could do the integration and do the inverse relation, you could obtain the solution. So I would say that sorry, the concept quantity will play the important role in this context, which you will see later that if you could find the concept quantity, is going to help you a lot in order to get the solution. All right. Okay. So, well, before we get into the integrable system, I need to provide you some basic background on the Hamiltonian mechanics. All right. So now let's talk about Hamiltonian mechanics. Okay. Given n-dimensional, yeah, maybe space, this one, did I call this thing? We should actually space of all the generalized coordinates. Yeah. This is a set of generalized coordinates. Okay. And then from this set of generalized coordinates, you can construct a new space here that we call cotangent bundle. Right. Okay. We should actually we have a set of P as well. There is a P variable that's called canonical momentum. And it's the Q, right? This is a set of canonical momentum here. Okay. And this space, I mean, this, well, you could think this is the manifold 2D, 2n. This is 2n d dimension manifold. And you could think this is a real line. You could think that actually your Hamiltonian is as a map from this any point on this cotangent bundle to the real line. That is you can think in that way. So you could think that your Hamiltonian, which is a function of P and Q, as a map, right, to the real line. Okay. So, well, with this, actually, another name of cotangent bundle is nothing but the phase space, actually. All right. Okay. So what we have here is we have a set of, it's too close. A set of first order, ODE, okay, which is actually this one. Okay, where I'm running from 1 to n. All right, this is known as Hamiltonian equation. All right, okay, this is a set of Hamilton, the set of first order 2n equation, right? You get, well, you get an equation of this and another n equation of this. Totally, you have 2n equation to solve. All right, all right, okay. So the next thing that I would like to talk is the Poisson bracket. Poisson bracket given a smooth function defined on this cotangent bundle or the phase space, this big F as a function of P and Q and the time as well, which is the member of or possible function on this cotangent bundle. We define, oh no, sorry, we not define that. Define that. If you look for the total time derivative of this F, you will get very straightforward. You do the chain rule, right? And you get this relation. Okay, and then you apply the Hamilton equation to the Q dot to eliminate the P dot and Q dot, right? And then you will get, so you will get Q H P QJ. Okay, you will get this one. And now we define this bracket, the Poisson bracket, in this way. So, well, this is again any function that actually define on cotangent bundle. Here, okay. Now this is nothing but the Poisson bracket. Okay. All right. With the property, let me put small area here. The property of the Poisson bracket, any function f and g, if you swap the order, you get the minus sign in the front. And there is another one. This is known as a Jacobi identity. Okay. All right. This is some property of the Poisson bracket. So once we now you can express this the total derivative of the function f with respect to the time in terms of the Poisson bracket now. Okay, let me do that for you. This is page number 6 now. So then what we have is this. Well, okay. And if f does not depend on time, on time explicitly, this means that your partial derivative of the f with respect to the time will be 0. Then what we have is the total derivative of this f with respect to the time is nothing but the Poisson bracket between the f and the Hamiltonian. Right here, you get this kind of relation. So here, I put the bracket here. We can somehow treat the Hamiltonian as a time generator. Okay. Yeah, because anything that if you put anything that actually define on the cotangent bundle in the Poisson bracket with Hamiltonian, you will get the time the time derivative of that thing, right? Okay. So next, we consider the derivative of this. All right. This is again nothing but a chain rule, right? And then you could, well, this is something, this is actually, this is one form. And well, you could think this is the basis for this one form. Well, if you don't know one form, that is okay. Just keep in mind that this is called one form, and then you look at the time derivative again. Here, which is actually can be well, let me move this obis a little bit here. Oops. I move it back here. Okay. So you could think that actually this is a product between this Kf by Kp dP alpha plus Q alpha and sorry. Beta this thing. Okay. And this bit, you could think this is the dual part of this one form. Okay. And then with this kind of way of writing. Okay. So is there any problem? Sivishai, can I continue? Okay, I continue then. So this way of writing the derivative, I am going to, well, I can put here in terms of this bracket, which is actually, this is in this way, where this fancy H here, it's is the Hamiltonian vector field. Okay. Okay. Well, but if you don't like, well, you can eliminate P dot and Q dot by using the Hamilton equation, right? Then you can put thing in this way, your Hamiltonian vector field. Okay, all right. So what we have here is that, the thing is that I just, well, in order to make this I would say in the product work, and you need this kind of relation as well to be whole. This thing is nothing but it's like the dot product of the basis in the ordinary vector space, but this is much more fancy, fancier, I think. Anyway, so well, now so what we could say about the way that we put things here. So you could see that actually what we have on this side is the time derivative of the function f actually defined on the cotangent bundle and explained in terms of the vector field that govern this kind of vector field that associate with the Hamiltonian. That it,
อาจารย์จอค้างหรือเปล่า
yes. Oh, okay. สิริชัยโจ้ครับจอค้าง Sorry, khôngทำไมอ่ะ Sorry guys, so let me do it again. Stop. ปัญหาคืออะไรเนี่ย
ไม่ออกจากไอ้ตรงใต้ปกเสื้อ
ได้ไง เอ้าคือผิดเอ้าไม่ได้อยู่เลย อะไรเนี่ย Sorry guys, there is a problem. Wi-Fi. Skin. Oop. Okay, sorry, I start again. Okay. Can you see my screen now? Everyone? Yes, okay. So I don't know when there is a problem happened. large page. Oh, okay, page 6. Okay, here, right? Okay, let me check again. So on this page, so I do again write the total derivative of the f with respect to the time here. Okay, and then I split it into two parts, which actually I put it into the like a dot product of the first part actually coming from this df, and another part I call is dual part of the one form. You could think this is nothing but a dot product in the ordinary vector space, right? And in order this dot product to work, you need this kind of relation, right? As well. Once you get this, so you could think that this you can put into this kind of fancy bracket, or the, somehow you could say, well, this is the Dirac bracket. But I don't, actually I don't want to say about this Dirac bracket because it's nothing to, we are not going to do thing here with the quantum, it's still classical. But anyway, when you could do this, then you define this total derivative of the function f with respect to the time as a hh here, at this big F, big X HF here, though where the big X here is nothing but the vector field, or known as Hamiltonian vector field. All right, okay. So the dynamics, so you could say that, so what we could say, the dynamic of F on this cotangent bundle with respect to time, okay, can be viewed as a chain of F. In this sense, this F, this is a chain of F, is nothing but a dF, right? Along the Hamiltonian vector field, actually. In this sense, you could say that there is a word flow here, right? Okay. Okay, right. Next. Now we define this kind of eta at the two bit of this thing, and then I define this j as this okay. This is nothing but it's called symplectic matrix. Yeah. Okay. So with this new notation, the Hamiltonian, no, not the Hamilton equation, okay, can be expressed in a new form, more compact with this one, or if you want it shorter, you can put it in this way, where this is you could think this is the derivative of tuple n. This is going to be very huge column matrix. Okay, this way. All right. Okay, so with this new way of writing Hamilton equation, so now we look again the total derivative of the f with respect to the time, right? And then we do nothing but the chain rule here. right? Okay. And then now this to this, okay? I'm going to get this equation, okay? And we know that actually this is have to be equal to the Poisson bracket plus the partial derivative, right? So then we write the Hamiltonian vector field as this one, okay? Or well, if you work out the multiplication between these two matrices, you will get the same here again. You're going to have this relation again back with this multiplication of these two matrices, okay? But I'm not going to do that because it's not that kind of difficult. But well, the matrix is a little bit huge. It depends on number n that you're looking at, okay? All right, so next. So I'm going to talk about one parameter group. Yeah, okay. Oops. Are you, well,
อาจารย์ครับอาจารย์ปิดไมค์หรือเปล่าครับ
oh, can you hear me now?
Yes.
Okay, sorry. Well, all right. So I start again on this page 9. Okay, everyone. So now we're going to talk about one parameter group. So after I introduce you the Hamiltonian vector field, right? Now next we're going to see the role of this Hamiltonian vector field. Okay. So this the dynamics of this Hamiltonian vector field provide a family of the maps, which is actually the map on the cotangent bundle itself, right? The initial point, yeah, which is actually Q0, P0 into a new point at some later time t, Okay. So as time flow, each eta is mapped further, and of course further, okay, along the trajectory that, well, in another language or in another is called in the integral curve. Integral curve. And in this way, the entire cotangent bundle, okay, is mapped continuously into itself, okay, by being pulled along the integral curve of this Hamiltonian vector field. Okay, well, let me draw you a picture. Suppose this is our cotangent bundle. All right, so this should be the initial point, and then this is the trajectory. Okay, and then this is some later point on this space, right? So there is a flow, or this is a direction of the Hamiltonian vector field, right? Yeah, actually going this way, as indicated by this black arrow here. This is the direction of the flow. Now, now we define this as a map, as a continue as the family. Oops, sorry. Family of mapping and write this way. So in this sense, it means that this thing is mapped into, well, the initial point is mapped into the later point by this action of this is mapped, or, well, you could think this is something that are actually acting on this one, and then you get this one, right? Okay, and we should satisfy this satisfy in the composition rule. Okay, this composition rule, all right, which make the family by definition one parameter group of transformation. Okay, yeah. So, well, what I mean by this one parameter group of transformation is that actually in this sense you have only one independent variable, which is actually t here, right? The t, yeah, which is actually the same with the t and s are, well, in the same equal footing. We have only one independent variable, the time, right? That is one parameter, that is a parameter in this situation. So with this thing, so you could think that actually what's happening here is that you map you could think that there is a map here by the epsilon to a new point, and then you get this is new epsilon, and you could do another map in the same portion. You get 2 epsilon again here, and then you could continue 3 epsilon, and then you do again until you get into the final point, something like that. And according to the composition rule, you can do the composition map here to epsilon, right? Yeah, something like that. This is the map that we have here. Okay, but the thing is that this map happening along the trajectory of the system on the cotangent bundle is actually along. Okay, okay. Hope you get the point. All right. So next topic is canonical transformation. So I'm going to use this city as a canonical transformation. So, well, the thing is that, as you well know, a choice of the cotangent bundle coordinate is not unique. It's not unique, right? Such that you could do a transformation from old set of PQ to a new set of PQ, which is actually I use this a big P and big Q here. Okay, but why we call canonical? Well, there is a condition that why is that? So well, with this notion, the way that we write the Hamiltonian way. So according to this canonical transformation, you will get a new set which I label by this tilde, this J, and you get also the new Hamiltonian, where this is the new Hamiltonian in new set of coordinate here, right? Where Q and P has been mapped to big P and big Q. And of course, big Q can be expressed in terms of the OP and OQ. And the big P is the same. Okay. Now, what I'm going to do is that, so let's look at this equation here. Let's put it here again. Okay. I do here. Okay. I do a kind of the coordinate transformation, and I get the metric M here. All right, so it should be K here, right? Okay. So this M is nothing but it is the Jacobian matrix, right? Actually, you probably familiar with this kind of, well, the way that you do the transformation, do you get the Jacobian matrix? Yeah, this is the same thing. And once you get that, so what we are going to have is L here, you get JLM, this, right? So because now for the next step, you apply this Hamiltonian equation into this, okay? And then you will get this relation, okay? And so write everything right? Okay, yeah. And then you're grouping it. So what you're going to have, okay? So you get transpose, okay? This one. So if you want to the Hamilton equation to be, well, to be the same or preserved, then it means that, so this thing has to be this one. So, and then you get the preserved structure. Well, I actually, this is I mixed the thing here. So, well, the way I put thing here, it should, you have to keep in mind, and when I put the index here, I mean the element of it. Maybe I should, well, there is actually should be the bracket here as well to make it to the matrix, right? Anyway, so now, what after we have this kind of relation, you see that actually after the transformation, your Hamilton equation is preserved, right? So yeah, so Hamilton equation preserved. Okay, so what we have is that under the canonical formation, the symplectic, symplectic matrix must be preserved. Okay, that's what we have. Okay, and then in this Hamiltonian context, okay, cotangent bundle or the phase space is called symplectic manifold. A symplectic manifold. Okay. According to this structure, well, when this, well, let us focusing more on what we mean, what I mean by this symplectic word here. Okay. Given a symplectic two form. Okay. Omega, we should actually sum P QK. Yeah. So here is the wedge product here. Okay. So this symplectic two form, okay, which must be preserved under canonical transformation. All right. To make things clear, I'm going to give you some example. Okay, like in 2D situation. In 2D situation, you're going to have P and Q. This is the O set of coordinate, and then you have P and Q. No, sorry, it should be another way around. The Q and the P, yeah. And then after you transform the coordinate, you get a new space that called P and Q there, and then you get this big Q and big Q. All right, this is under the canonical transformation. So you could think that actually this omega is a wedge product of P and Q, which is this wedge product is nothing but the area, right, of this element that I just do the shade here. We should actually have to be the same with this new element in this new space, right? Okay. So the area must be preserved under the canonical transformation. So, well, I hope you get the point here. But for this thing, you could think that actually, so the area for each pair of the PQ must also preserve. This is a sum. So this is a sum of every single pair of PQ in your Hilbert space. Oh no, not Hilbert space. Sorry, cotangent space. That is a thing. All right. Okay. So let me do a summary for you. So what time is it now? Okay, it's up almost 9 o'clock. Okay. Summary. Okay. Cotangent bundle. Or phase space. Okay. Is defined as this one, omega and Hamiltonian. You need this manifold, which is actually equipped with this symplectic two form. Symplectic two form, and also the Hamiltonian. All right. These three ingredients give you this kind of, well, symplectic manifold actually. Hamiltonian as a map. Okay. So let me draw you a picture again. Suppose this is our cotangent bundle. Well, if you start, so you could, well, all possible trajectory with different initial condition. So this is a flow along the trajectory, right? That governed by the Hamiltonian vector field. All right, okay. And any single point here is labeled by P and Q. And then, of course, your Hamiltonian is nothing but the map into the real line. Okay. And then on this trajectory, you could do a mapping, as I said, as I just give you a definition by this vector field. This kind of T, maybe something like that. Okay. Hope you get the point. So now with this kind of way that I introduce this omega thing, the two form, a symplectic two form. So you, well, let me, I think this is, let me, I need a little more, I need more space here. Then I put the H here now as a map here. So you could write your Hamiltonian equation labeled by this omega now, where this is the symplectic gradient. Okay, such that, okay, so you could think that actually this is nothing but the gradient flow for Hamiltonian on manifold on this cotangent bundle order on this manifold, but with let's back to metric, symplectic form, omega larger than Riemannian metric. Okay, all right, that is the thing. Okay, I think I kind of give you some idea about basic Hamiltonian mechanics. Okay, we are going to use this kind of whole ingredient again later when we talk about integrability actually. So the next topic is about action angle variable. So I'm going to put this as AA, okay, action angle variable. So, well, we know that under the canonical transformation, you could find a new set of coordinates, right? Which I label by I and theta. If this is, well, let me put here. If theta is the cyclic, okay, coordinate, okay, then your new Hamiltonian is a function only the I, right? It's a function. It depends on solely on I, right? Okay. Then the Hamiltonian equation for this new coordinate will give you this, right? The time derivative of the I will be 0, and then your I is nothing but constant, right? Constant. Why? The theta dot here should be I is a function, is some function of I, and then you see that this is the first ODE, right? And the I is a constant, so it means that you can do the integration. Okay, and then once you finish your integration, you're going to have t plus beta here. Beta is a constant of integration here. So what it means that, so, well, with this kind of structure, you can solve your problem by quadrature, right? It means that you can, well, explicitly solve the problem. And let me, okay, with this structure of new Hamiltonian H tilde, which is actually a function of I. The problem can be solved by quadrature. Okay. And of course, this type of coordinate is called action angle. Action angle variable. Okay. Where this is action, this is angle. Okay. All right. Okay. So the main point is that if you could find a nice transformation from an old set of coordinates to a new set of this kind of condition that I put on this page, you could it means that you're going to solve the problem explicitly. All right. Okay. That is a thing. But well, the way that you could find is not that kind of necessary. It's not that easy at all. I mean, well, the way that you find the transformation. Okay, let me give you example. Okay, give you example on simple harmonic. Okay, which is actually this is simple harmonic oscillator. This is the Hamiltonian for a simple harmonic oscillator right here. So from this relation, I can find the P, which is actually, oops, sorry, m omega square here, right? Okay, and action variable I is 1/2 pi integrate closed loop PDQ here. So I give you this kind of the formula first, and you will see later why I put it this way. Okay. So what I'm going to have is this. So what you need is the integration from the initial point. Let me do. Let me start new line here. It might be better. 2 pi. I start from minus q to plus to just q. M omega square q dq here minus q to q is that correct? Yeah, I think so. Yeah. Q, right? Why is that? Because, well, you could look at this Q and P here, and then this the trajectory will take place on this ellipse, right? Okay, you start with Q0, and then this is minus Q0 here. Okay, and then this bit is nothing but the first half here. Okay, and this bit is the second half here. Okay. Okay. And then we using the fact that you could solve the order of integration, like sorry, y is going to be, well, minus q0 f dq, right? So then you can reduce the number of terms of in the bracket into just single term. So the I going to be 1/2 pi integrate from starting from minus q to the plus to the q naught to the minus q naught to the plus q naught m square. Okay. And well, this you can do the integration in here, right? And then, well, well, from this relation, let me put here from this relation, you know that your q naught is 2h square, right? This is called turning point. Right, turning point. Okay. So now, if you want to do the integration of this thing, it's not that kind of simple. You need to use some kind of technique called substitution, right? So what we are going to do, which page now? 16 or 17 here. What we are going to do, we introducing Q naught psi phi, and then dq equal to Q naught cos psi phi d phi, right? Okay. With this new variable phi, so your I become 2h over pi minus pi over 2, pi over 2 phi, and then you get h over omega, and then you could say that actually, you see, right, your h is a function. Now your h is a function of I, right? Okay. And then once you get this thing, so you could solve for you could solve we look at for the Hamiltonian equation, right? The Hamiltonian equation. Okay, I dot with this new h here, which is actually 0, then your I is a constant there, yeah. And then your theta is, which is actually the omega. Okay, and then your theta is nothing but omega plus delta. Delta is equation. Well, then you get the answer now, because yeah, this is, well, you solve the problem. It means that if you could find the set of action angle variable, you can solve the problem explicitly. That is the thing, right? But the thing is that, let me point out, is that let's look at, oops, sorry, let's look at P. No, this should be Q, and this should be P. So we have ellipse here, right? And then we have the point PQ here. And then under the canonical transformation, you get a new space that you call theta and I. Okay. But the theta is, there is a periodicity condition with it, right? Because it's the angle, and your I is the constant. So it's going to be constant along this line. So if you divide this by the period, so it means that this whole period is the same with this whole period. It's the same again with this whole period. It means that actually this point, this, oh, I'm going to use black. This point, this point, this point, and this point are the same, right? Same. With this kind of condition, you can impose the periodicity condition, and you will get, sorry, this is 18, right? So you will get, oops, sorry, yeah, a circle, which is, you can put the radius as a I, right? This is S1 or T1 or the torus, right? Well, but this is, okay, I would say that this is, would be invariant torus. Why is invariant? because the radius of this torus is constant. That is the reason why it's invariant. And on this torus, you can think this is the new space for your system. You are now no longer P and Q, or right anymore, because you do the canonical transformation. You get a set of action angle variable, which is actually I and theta here. But with this property of the theta, you can impose the periodic city condition, and then you can get a new space, which is actually this invariant torus. In this, on this particular case, for the harmonic oscillator, which is you get a circle, which is actually one-dimensional torus. Okay. So let me put remark here. So the existence of the action angle variable imply the existence of the invariant torus. Okay, and of course, with action angle variables, the system can be solved by quadrature, and indeed it is integrable. Okay, this is the key message actually. Okay, let me say it again. The point is that if you could find a canonical transform, or actually if you could find a set of action, it means that it's guaranteed that you're going, well, your system can be solved explicitly as this kind of particular example. And then with this, the existence of the action angle variable, it implies the existence of the invariant torus as well. Okay, all right. So what time is it now? I think 9:18. So I think I'm going to take a break, 10-minute break, maybe. And then we what time is it now? I think it's now like 9:20. So we're going to continue on 9:20, 30. Yeah, maybe. Okay, anyway, let's take a 10-minute break, everyone. Okay. Okay. I hope everyone have had a good 10-minute break. All right. So let's continue about this topic on integrable systems. So I hope everyone back already. Let me say it again on this page that I emphasized before we take a break. Actually, the existence of the action angle variables implies the existence of the invariant torus, right? If you could find the action angle variable, it means that your system can be solved by quadrature, and then indeed it is integrable. But the thing is that, but such canonical transformation to get this action angle variable is non-trivial, I would say. It's not that easy to find at all. For this particular example, it might not be that kind of difficult. But if your system contains a lot of degree of freedoms, a lot of variables that you have to deal with, is not that easy at all. Then, well, we have now another way. Okay, now we have another way. We call Liouville Arnold theorem. Okay. So according to this theorem, the integrability is defined in terms of existence of the invariance. Okay. Well, I did mention this kind of the role of invariance at the beginning of the lecture, that this kind of concept quantity or the invariance will play an important role in this context. And then you will see now implying the existence of action angle variable. So well, we do kind of inverse process. Instead of looking for the action angle variables, you're looking for a set of invariance. Once you get a set of invariance, and somehow you could find a way to obtain the action angle variables. This is kind of indirect way, not the direct way. Okay. Okay, let me state the theorem. If, okay, in Hamiltonian dynamical system with n degree of freedom, there are also known n first integral of motion. Well, the integral of motion is nothing but the constant of motion. That is the thing. Is f, this set of f. I call this is as a set of constant of motion. Oh no, integral of motion. Sorry, actually define on this cotangent bundle, which are independent and in evolution. This means that by this word in evolution, this means that the Poisson bracket between fi and fj, which is that I not equal to j, has to be 0. Okay. Then there exists a canonical transformation to action angle variables I and theta which is actually I1, I2. I'm sorry. Let me write again carefully. I1, I2, IN, theta 1, theta 2, theta n. Okay. Yeah. Where I is a function of Hamiltonian. Okay. In which, okay, I'm running out of space here, so I start again on new page, in which the transformation, which is the transform Hamiltonian, is dependent only upon the action variables and the angle variable evolve linearly. Okay, in time. Okay, that's the equation of motion can be solved in quadrature. Okay, what I mean by quadrature is that this kind of structure that we have here. Okay, so well, it's a little bit long theorem, but but this thing is that, so well, let me say it again. So first, if you could find a set of invariant, this F, okay, which is actually a they are function that defined on the cotangent bundle, and they are in evolution, or the Poisson bracket between them vanishes somehow. Okay, so there exists a canonical transformation that you could get somehow action angle variable right out of it, and then with that action angle variable you can solve the system by means of the quadrature. Okay, so next, now we have a theorem, then we're going I'm going to give you a proof. Okay, let do the proof. Okay, the motion will take place on the n dimensional hyper surface. Okay, what I mean by this n-dimensional hypersurface, because it is a surface that associated with this whole invariant, actually this is called C1, C2, and then of course you have Fn, PQ. This is okay. This is give you the hypersurface structure, and taking the assumption that the determinant of this Fj Pk not equal to 0. Okay, we can solve for Pi such that it means that somehow you can express your momentum in terms of Q and C. All right, somehow. Well, if I would recall the in case of the simple harmonic oscillator, C in this case is nothing but the Hamiltonian or the energy, right? It's a function of Q here. So it means that your momentum can be expressed in terms of this H minus B as a function of Q here. Okay? Which is your H is nothing but the C here. Okay? This is very trivial example. All right. Okay, so what page? 21st now. Now, what we now differentiate the identity. Identity Fn equal to Cn. Okay. With respect to Qj. Oops, sorry. J. So going to get is Pk Qj equal to 0. Okay. This is very straightforward. The next step, I'm going to multiply the whole equation with this thing. Fm Pj. Okay. Qj. Mj. Okay. Fm. Fn. Fpk. Fpk. Fqj equal to 0. So what I did is I multiply this whole term here into this equation. So we get this one, and then I label this as a Lux equation. Now, if we swapping index such that Mn, okay, between M and N, so you're going to have N, Pj, Fm, Qj plus J plus K, Fn, Pj, Fm, Pk, Fpk, Fqj equal to 0. I label this is as double Lux here. So next, what we're looking at is the difference between this double Lux and a Lux equation. So we obtain well, it's a little bit long proof, but so it's worth to know. Oh, it's too long. Okay. Okay, I finished this. And then you see that actually the first term is nothing but the Poisson bracket between Sm and Sm, which should actually give you 0 involution, right? Involution. Okay. And the second bit, the second bracket for this particular term, you can rewrite it in this way. You can swap the index between k and j because it's the dummy index, right? You can do that, right? You can swap k and j. And then at the end, you will get what we have is some j, some k, f m over pk, fn over pj, pk, pq, pj, pqj equal to 0. All right, this is what we have here, this relation. And since we have that the determinant of this fn not equal to 0, then this what we have from this equation is that qj, qj, pk equal to 0. This is what we have here. I call this is the pyramid equation. Okay. Now we got the pyramid equation, and then, well, what we can do with it, let's see. Okay. Now we consider the Stock Theorem All right, this is the battery. This is, well, this is the manifold that you are interested in. And then this is a battery of this manifold. So if we look at this carefully, so this is the battery, and then this is a manifold M, right? So the Stock Theorem tells us that actually, if you make a circulate arrow here, you can divide it in. You can make it right. So what you have is here this small curve thing that happening on each of the small area here, right? And then the internal link or here, you will the arrow will cancel each other, and then effectively you will get only the outside circle. That is something. Okay. So we knew that this kind of thing at the p component, ijk, k, qj, pj, no, sorry, should be q, right? qk. Okay. This is Lewy symbol. Okay. And then you look at this, well, this is what we had before and in the previous phase, right? Okay, so then what we have now is that any closed loop integration of this closed loop of p dq equal to p dot dq dot equal to 0, right? Okay. Well, this I would like to make it any closed closed curve that can be deformed to point. Any closed curve that can be deformed to point, or is called contractible curve. Contractible curve. Okay. On Tn, or the torus of the dimensional in dimension in, right? Okay. So and let me draw you a picture. 24. Suppose this is to be your Tn. The contractible curve is the curve, the closed curve like this. This is so the curve, this curve, this can be contract. You can make it smaller into the dot, right? Something like that. Or this kind of curve. Okay. You can make it smaller and smaller into the dot, right? Something like that. But there is a curve like this. This is non-contractible curve. Contractible curve. Okay. This is an example. Because, well, you cannot shrink this curve into the point. Well, this particular curve here. Then for any enclosed curve which cannot be contract, down to a point. Okay, this does not, does not vanish. Okay, or is not equal to 0, then we define. So let me make thing here. Okay. So let me define this action variable into this way. Okay. Right. Okay. Is the closed curve. Okay. Non-contractible. Okay. This is non-contractible closed curve. Okay. Or is another name is called K basic cycle of the torus. Tn. Something to do with the sundown. We are not going to say that in detail. So, well, okay. So it means that this closed curve is parameterized by this variable. We should actually on Tn, where j 2 pi constant if k not equal to j. Okay, right. This is a way to define things. So you may ask the question that, okay, let me draw you again a torus. You may ask that, okay, at first I might choose this kind of non-contractible curve, this kind of gamma k here. What if I choose a new curve, this one called gamma k palm here? Is it going to give me the same action that I give you here? So the question with a different non-contractible curve like this, going to give you the same action or not? So, well, let's see. Okay. Well, if you look at this in the picture, you're going to see that actually these two curves form a tube, right? And then there is a surface associated with it. There is a surface of this tube, right? Okay. And you can call this with the area surface area. Okay. Suppose this is, well, for example, T2. So using the Green theorem, okay, so we have that A, right? Apply the Green theorem, which is actually A Q2 dQ1 dQ2, right? So which is actually equal to 0. Then it means that, well, they give the same action variable ik. Okay. So it doesn't matter which loop that you choose, then it's going to give you the same action. Well, but you have to be careful because for this particular, like a T2 here, like this donut shape of, let me draw it again. There are two different fundamental contractible curve, right? You have to be, okay. You have to be careful. Here is one type of contractible curve, and this is another type of contractible curve. You have two type of fundamental contractible curve for this T2. Okay. Now put this inside. So the action IK are also first integral as okay. Okay, only depends on Cn, right? Actually, Fn, okay. And then you know that actually Fn are first integral, okay. Then this quantity is constant somewhat, okay, because, well, if you look at this integration, the variable that's going to be disappear after you finish the integration is a q, right? Then at the end you left with the c, and c is something to do with the fn. Then at the end you get the invariance, right, associated with the, well, this action variable here. Okay, this is the reason why your ik is first integral. Okay, next. Okay, next we look at Boson bracket, boson commuting, okay, of this II and ij. So, well, is going to be a little bit, yeah, a lot lengthy somehow, but well, I can try. So what you're going to have is if Fi, Q, K, Fi, J, S, P, K. So what I did here is nothing but the chain rule actually, but yeah, is I need to spend a little bit energy to finish this line. And it's yeah, QK, I think. Yep. Okay. And then you pull out all the common terms, and then you will get, once you pull out all the common, so you will get IJFS, and then you will end up this boson bracket, which is actually 0. Then you get this 0, right? So now we can show that actually this now also involution as well. Okay. All right, then. So far, so we complete in order to construct the action angle variable, right? So let me repeat again. So first, I assume that there is a set of this invariants, right? That form the hypersurface. And then now I construct I do some mathematical trick, and then at the end I could define the action variable here, right? And then I can show that this this set of action variable, they are in evolution, right? Yeah. And then this coming from, and this action variable actually coming from the way that we consider the closed loop of integration of the p function of the non-contractible curve, or fundamental, what is called the name again? Fundamental basic cycle of the torus. Okay. So the next, what we need to do is that, so we need to look at for the angle variable. 27. Next, we will construct the angle variables, right? Theta k. Okay. So what we need is that we're going to use a generating function. This S. Well, I haven't mentioned about generating function in when I talk about canonical transformation, but you have to keep in mind that there is a generating function associated with each of the canonical transformation. All right. There are 4 types of generating function. So let me put here note canonical transformation PQ with S QP and maybe frequency. This is a property, and QK PK not equal to 0, and you also have a relation of the generating function in this way. Okay. This is this is the basic ingredient from the canonical transformation associated with the generating function S here. There are 4 types of this generating function that I recommend you to go if you want to know more about this generating function. You can look at the course book on mechanics. Okay. Now we continue where Qj is some chosen point on the torus this definition does not depend on a path connected between Q0 and Q as a consequence of IK and Stock Theorem. Okay, so what it means is that this whole integration here, it doesn't depend on the path that connect between the initial point and the final point. Okay, let me draw you a picture. Let me give you a picture. Suppose that again, this is the torus that you're looking at. This is supposed to be Q0, and then this Q. Okay, and the path that you consider can be go here and go at the back of this torus and end up at the Q point there. And they call mu1 here. They call this part mu1. So you could have your S labeled by this mu1. Okay. Q0 to Q. Sorry. EJ, QJ. Okay. And I do label here this by mu1 because we consider the integration along this path mu1. But you could go from here and end up there by the black part. I call mu2 there as well. Okay, you can do that. So then what I can do here, I can add this Q0 Q with the mu2 in it, right? And the same, and then I subtract out the same quantity again is the mu2. Okay. And then what you can see that if you combine these 2 terms together, what you're going to have is a closed loop, right? The closed loop of mu1, mu2, I would say, okay, of some pj, dpj, and the s of mu2. Okay, let me use different color then. Oh, sorry, because I need to emphasize that actually we have a new part, the black part here. Okay, mu2, and then of course this is 0, right? We proved that because this closed loop is contractible. This contractible, and this whole integral going to be vanish, right? Vanish. So it means that it doesn't matter which which is kind of we see that this is called path independent property, right? So your S here does not depend on path connect between Q0 and Q. All right. So as long as it's, well, and then something to do, well, as long as you can, oh, there is something to do with the homotopy property as well, because you could think that actually this blue part here, here can be continuously deformed to be a back part here, right? I am going to label this kind of continuous deformed by this lead part here. Continuously deformed. Okay. This. Okay. There's something to do with homotopy. Homotopy, I think. Okay. Property. Okay. All right. So now what we have is the S function. Is the integral of this thing. Okay. Ln K next 29. Okay. So we could have like a part that look a little bit strange, like this one. You could have a part that actually connect these two fundamental circles together, and then that point, this should be your Q0, and then this should be your Q. All right, and then this is called gamma and gamma K here. Okay. So what will happen if you have this kind of strength curve or part here? So your S is going to be a kind of a joint, a joint closed curve together, and then open curve. That this means that you can separate it out. This is called C. This is C. Okay, you can split it out, and then this is give you closed curve, and then this is give you another closed curve, right? And then these two are non-contractible. Non-contractible, right? So these two terms give you nothing but the action variable, right? So this means that, so you get again the S plus extra constant, which involve the action variables. Okay, that is the thing. So then this means that the closed curve will give extra constant, okay, to the spelled wrongly, generating function. Okay, hope you get the point. With this kind of structure, now you can use this generating function to compute your theta. Then theta k could find from the S by looking at the derivative of the S with respect to the I. So you get theta plus 2 pi. Okay. All right. So you use this kind of relation here. Okay. right? And then you get this one. And then of course this is, well, give you periodic periodicity condition. And of course this theta is it's an angle variable in this sense. Okay. Okay. So if you want, actually for this particular example, if you are into torus, two-dimensional torus, you're going to have another theta that's called plum. So you're going to do the derivative with the plum. Then you're going to get again plum with the 2 pi, because there is ik palm here, right? Again, it gives you the angle property. So the canonical transformation Q and P, okay, and this PQ I QP, right, such that, okay, they are defined by a generating function invertible, thus equal to 0, and of course this angle goes on have just give you the delta function. And then with this setup, with this ingredient, you could, this is page number 31st, okay. Yeah. And the Hamiltonian equation actually could read here. Okay. All right. This is your new Hamiltonian H-tutor here. Okay. As a function of I and k, and if I, k are constant, as we wish for, like to be action angle variable, this whole equation will be reduced to this just a set of first order equation, and your system can be solved by quadrature. That is the thing. All right, okay. So now we finished in order to construct the angle variable, all right, by using the generating function of the canonical transformation as here. All right, let me do the summary for you. Okay, summary. Okay. So you need to search SEAR. You need to search for a set of maximum invariance F1, F2, Fn here, okay, which are functionally independent and in evolution, it means that Fi, Fj, boson bracket equal to 0, I not equal to j, right? Number 2, this implying that there exists a set of action angle variables also invariant torus. All right, okay. That's what we got from the theorem. So if you have a set of invariants, I call this F, which is actually functionally independent, and in evolution, so you could find that implies that there exists a set of action angle variable and also invariant torus. That is a thing. So it's the sense that actually this is the indirect way to show that actually your system, you not need to looking for the set of action angle variable directly, but for instead you're looking for the set of invariants, maximal invariant, which is property functionally independent, and in evolution, if this set of invariants satisfy this kind of property, you can say that, oh, there must be a set of action angle variable and also the invariant associated with it, and you might for that action angle variable, you know that there exists that enough for you, right? Okay, now come to the question. I put the word searching here. You may wonder, how could we get this type set of maximum invariance? We're going to look at this later, a little bit later, but you have to keep in mind how could we get that? Because, well, there is a difficulty with the action angle variable, because I just mentioned that actually there is no trivial way that you could obtain an action angle variable trivially, right? If you're lucky, then you could get it. If you're not, then you're not, right? But now I continue with the main feature of this the key feature, the Hamiltonian commuting flow. Okay, this is the key feature of this Liouville integrability that I just mentioned to you before. Okay. So, well, since the F, this set of F, that's actually defined on this cotangent bundle right here. Now we can treat them as a set of Hamiltonian. Okay. So somehow we call this Hamiltonian hierarchy. Okay. You could think in this way. You have n Hamiltonian hierarchy. Okay, we should actually equip with the property or this boson between different edge involution, actually nothing but involution property. Okay. And within in this set, the standard Hamiltonian is one of them. Okay. What I mean by standard Hamiltonian is that the way that we put this here, what I mean by the standard Hamiltonian. Okay. Can I just take a 5-minute break? All right. I need to go to toilet. Okay, let's take a 5-minute break and then we continue. Okay. Okay. Sorry. Okay. Okay, let me continue. So let me continue from the standard structure. As I mentioned earlier, the Hamiltonian can be viewed as the time generator. Yeah. As this one. Right. Where this box is a function that actually define on cotangent bundle. Okay. Then with this kind of picture, now we have n Hamiltonian or the Hamiltonian hierarchy. So it somehow is mean that so we have also n time parameter. to deal with. So we have now multi-term. Yeah. But again, only one physical term. What I mean by physical term is the one that associated with the standard Hamiltonian. Okay. All right. Okay. Now, given any function actually defined on this cotangent bundle, and I look at the term derivative of this f function tk, which means that I'm going to look for the Poisson bracket of f and hk, and if I look at the term derivative with TL, then I do the same with the HL, the Poisson bracket here. So what I'm going to do next is I'm going to do the derivative in this way. Okay, so and K L F what I have here. Okay, all right, okay. And then we look at the difference between these two. You're going to have okay, and then you apply the Jacobi identity, I think. Jacobi identity. So you're going to have okay. So and this one give you 0, right? This Poisson give you 0, then effectively you get 0 here. This is called somehow Hamiltonian commuting flow, and then this is called Hamiltonian commuting flow. Okay, this kind of feature. Then the order of evolution does not matter for function f actually defined on this cotangent bundle. Okay, so if you I could try to give you a picture like this. So this is cotangent bundle, and then let me define this is a flow. Okay, flow H K, and then there is another flow. Okay, this is for HL. Okay, what we have here is let me use maybe yellow color. What you have is a map. Actually, oh no, it's too bright. Maybe this color, this kind of map, and then you map from this. Suppose this is your starting point. You map go to this point and then you map again to this point. Okay. So it means that you hope by using this map TK with the Hamiltonian HK. Okay, and then you map again here with TL with Hamiltonian HL. Okay, and it's equivalent that you go from here with the map TL first with Hamiltonian TL, and then end up here with the map TK with Hamiltonian TK. Okay, right. Okay, and then well, you could think that this if I make this thing small enough, you could think this is like a parallelogram. Yeah. Right. Okay. So well, what we have here is a consistency of the mapping here. So let me put 36. So what I have is this is TK L HL equal to TL XS TK XS SK. Okay. All right. This what we have from this commuting map. Kind of. This maybe you can call this commuting map. And then this well, you could think that the whole structure is something to do with n parameter group. Yeah. Instead of one parameter, now we have n parameter group. Commuting, or maybe you can call it compatible. Okay. So which is actually this compatible map equivalent to the Lie bracket, but well, I haven't give you a definition of the Lie bracket that yet, but I just let you know that actually this is a commuting Lie bracket. Okay. Okay. Which means that these two vector field, I mean XL and XSK, will complete the parallelogram, right? Parallelogram. Okay, that is the thing. All right, hope you get the point. So this is the main feature of this Liouville integrability, and it's called commuting flow, right? And it's, or maybe this you could construct the commuting map or compatible map, and you have now n parameter groups, right, instead of one, right? Okay. Let me continue a little bit more. Okay, next topic is Lux pair. Okay. So why we need to, well, we need to look for the Lux pair. You will see a reason in a moment. Okay, let me introduce you first what is a Lux pair. Given a pair of matrices, it's called L and M, satisfying this so where is a function of maybe x or maybe q and t. Yeah, okay, is called auxiliary function, and lambda is a constant. Okay, with this couple equation, we could we then have this equation M and L called Lux equation. Okay. Okay, now we're going to prove it. How could we get the Lux equation? So what we're going to look at, we're going to look at the derivative of this relation. Okay, the L part here. Oh, right. So the thing is that, so this L can be called the spatial part, and we call temporal part. Okay. So now we do the derivative, and so we get dl by dt psi t, and then you pull out the lambda, you get the derivative of the psi here. Okay, and then you apply again here and here. You apply the M equation, so you will get dl by dt psi plus ln psi psi here. Okay, so now since this is a constant, you can move it inside this way, and then you get ml psi, right? You apply again here the L equation, right? So finally, and so you pull out the common term, which is actually psi, you will get ml minus lm, which is actually the metric bracket. Oh, sorry, the metric bracket. This thing. So this finishes the proof, and then you get the Lux equation. Okay, what is the use of Lux equation then? So the Lux equation will give the equation of motion. Okay, so this means that we do not need to deal with the Poisson structure. Okay, if you have a Lux matrix L and M, and then you could use it to compute the equation motion, right? Which is actually the same one that actually you got from the Hamiltonian equation. And then you can use this Lux equation to compute invariance. This is the reason why I introduced you the Lux matrices. So let me go back a little bit for here to this pairs. I emphasize the word searching and how, right? Now I'm going to give you the answer. Okay. So if the X is an invertible metric U, which is a function of t, such that LT to U, UT L0, UT inverse T, and M such that U invert. If there exists this kind of matrix U, we find that the time derivative of the trace of this L to the power n of this equal to trace of the L to the power n at time 0. Okay. So let's prove it. Okay. Let's do the trace of the L. T. Trace U, L0, U inverse, right? So because of the property of the trace, you can swap the order of the U. You can swap order of the U, right? And then you get one there, you get identity there, and then you get trace of the L0. Okay, so this is trace of the L1, L to the power 1 here. Very trivial. Then you can here for the Ln t. So because Ln t is you have Ln multiply itself n times, right? Okay. Then so what you need is L0, U L0, U, and then U L0, U inverse here. Yeah, right. So this is going to go away with identity matrix, and then you will end up with U L0, L0, U inverse. This is n time. Okay, and then you apply again U inverse L0 to the power n. Okay, and then at the end you will get again. So this means that this is the same. The trace of the L to the power n at time 0 and the time t is the same thing. Then this must be the invariant quantity, right? Implies that okay, we should actually we call Fn. Invariance. But for our convenience, so I'm going to put 1 over n there for our convenience. Okay, just constant, it doesn't matter. So let me give you an example. Okay, let us focus again was simple harmonic. Oscillator. So given, I give you I give you a Lux pair of this for the harmonic oscillator. Okay, and then you use this L and M, you put it into the Lux equation. Okay, this Lux equation gives you this P dot minus P dot. Okay, so if you compare these two matrices on both sides, going to give you this component and this component going to give you this equation. Okay, and then this component with this component will give you P equal to Q dot, and the rest will give you the same equation again. And then this together, you're going to have which is actually equation of motion of the system. That is a thing. All right. So, and then we now can use this L to compute the invariance, which is actually, if you look in the trace of the L, square actually, right? So it's the trace of this matrix. If you compute the L square, you will get this matrix. And the trace is nothing but you get okay, I think you get 2. Okay. Right. This is nothing but your, well, Hamiltonian here, up to the multiplication of some constant. So you get the Hamiltonian from by computing this L trace of the L square. Okay. So you get, well, this is very trivial example. So my conclusion is that, so this harmonic oscillator is a very good example because it's integrable. You could find a set of action angle, right? And there is an invariant torus, and you could find the Lux pair, and then with this Lux pair you can compute the Hamiltonian again. And that is the thing. Okay, this is the reason why the harmonic oscillator is very nice example in physics, because you can do a lot of things with it, with this harmonic oscillator, both in quantum level or in the classical level. Okay. What time is it now? So, well, I think right. Okay. So let me continue a little bit. I think I could finish this early too. Okay. So let me give you another example, which is much more complicated. If you compare with the harmonic oscillator, and the example is called Calogero-Moser system. Okay. In short, CM system. CM system, which is one-dimensional many body system with a repulsive pairwise interaction. Okay, the Hamiltonian is given by this one. FQJ IJ, okay, and we set mass equal to 1 for simplicity, and where this Fx equal to G square or X and coupling constant. Okay, so the equation of motion of this system is this one, J equal to N, but J not equal to I, F prime. What I mean by prime is a derivative with respect to its argument of this function. Okay, this is the equation of motion. So for this particular system, I can give you a Lux pair here, which is actually Pi EII plus IJ and Let me change my index, the way that I put the index a little bit, because there is an imaginary quantity here. So I put the k, and then there is I, k, l, k, l, okay, k, l, okay. So g a squared minus a. And m is a, e k k pound square k pound n minus a kl n kl kl square. Okay, so this is ML matrices for this Colorado system. So the way that I put the E quantity here is the way that we look at when we construct a matrix. This is the place that you're that going to sit in the matrix. This is I and J, something like that. Okay, with this, well, you can check yourself that actually this give you equation of motion. Okay, I'm not going through that because, well, it's not that kind of, well, it's not that kind of difficult, but you need to spend a little bit more energy with it. Anyway, what I need to do is to compute the invariance, right? I need to computing invariance. Okay. For the first one, F, I'm going to look at this one, which is actually the total momentum. Okay. And F2 over 2 test L squared. So, well, I actually did that for you, that I'm going to give you right away what is the L square. Okay. PK, EKK, KL, K not equal to L, IA. So this I is not the index, but the imaginary quantity. KL, PL, EKL, plus, well, you could try it yourself and see PEKL plus MN L, M not equal to N, and M not equal to L, I square, A square, QM, QN, MN, yep, and QN, QJ. So I think I put the wrong here. It should be N here. It should be L. Okay. E M L. Okay. So you can try it yourself at home, and then you do the test. So the test will give you, well, 1 over 2 sum of the P square and KL I QK QL square, right? K not equal to L. This is the Hamiltonian. Okay, So your F2 is Hamiltonian, and you can go further to compute F3 until you get Fn. But we are not going to do that because it's going to be very huge computation. But I just give you the idea actually. If you have the Lux matrix, you can use it to compute the invariance. All right, that is a thing. And then in those set of in the set of invariant, the Hamiltonian is one of them. Okay, so let me go back a little bit here. Let me give you idea again. So now we talking about the Lux pair right here. Okay, so given the Lux pair, or L and M, L is a spatial part and the M is the temporal part. Why is called temporal? Because the action of the M, when you act on this precise function, you get the derivative with respect to the time. That's why it's called temporal part. But the spatial part is kind of, well, actually it should be some kind of derivative with respect to the Q, but this we impose some kind of special condition on it. That then with this couple of the equation, you will get Lux equation, as I did the proof here below. All right, and then with this Lux equation, you can get motion without doing anything with the Poisson structure. This is one thing that you could have. Another thing is that with the L matrix, you can use the L matrix to compute the invariance, which is actually the trace to the power n here. All right. And then this is a proof that actually trace of the L to the power n is invariant, right? And then I give you this example, simple harmonic oscillator, which is actually, this is 1 degree of freedom. This is 1 degree of freedom. I mean, just n equal to 1. This is the reason why you have only one invariance in this, which is actually the Hamiltonian, approximately up to the multiplication of the constant, right? You have only one invariance in for the harmonic oscillator, which is actually the energy or the Hamiltonian itself. Okay, but for this system, Calogero-Moser, which is actually the system, the one-dimensional many body system with the n particle in it, with the repulsive pairwise interaction, and then this is kind of Hamiltonian. So here you, in this situation, you have n degree of freedom. So you expect n invariance, right? That's what you expect. And then of course, with the given this L and M, so you could use it to compute the equation of motion. If you don't like L and M, in order to get the equation of motion, you can use Hamilton equation to compute that as well. Right? Then you get the same, exactly the same thing. And with this L matrix, you can use it to compute all the invariants, which is the first invariant for this Calogero-Moser system is the total momentum of the system, which is actually this one. And the second one is nothing but the Hamiltonian itself. And the first one is going to be, well, the structure is going to be like this, very interesting. The first one is called something like p to the power 1. The second one is going to be something like p to the power 2. The plus something p to the third to the cube, okay? And you can expect that actually to the fourth here is some more complicated. So the Fn is going to be something like, there must be some constant here, but we just ignore it and then complicated. So all this is the reason why this is the potential thing. Okay, this is the reason why we call this one as a Hamiltonian. Okay, because the way that we define the kinetic energy right here, we define the kinetic energy with p squared. But if you go beyond f2, you see you get t to the third here, to the fourth here, in the end. We don't know what is the meaning of this kind of power of the p. Then, you can treat them as the Hamiltonian as I mentioned, but it's not that our kind of standard Hamiltonian that we use, as I mentioned, is actually the standard Hamiltonian is nothing but a t plus v, and the t is p squared over 2m here, right? That what I mean by the standard Hamiltonian. Okay. But anyway, all of these are invariants. Okay. Let me do the summary for you. Yeah. Before I stop, I think I do a very good time here. I'll give you a lecture. 1 hour ahead. Okay. All right. This is 45, 46. Okay. I give you a summary here again. So let me give you a tiny cotangent bundle. It's actually PQ here, maybe. All right, maybe. On this is kind of hypersurface somehow. You could think that this can, on this particular manifold, this is a 2n B manifold. Okay. There is a flow associated with it, right? This is maybe the flow. Associated with the first Hamiltonian of your system. Okay, in this particular direction on your manifold. Okay. And you could have on the same, this one, you can have another kind of flow, okay, associated with the second Hamiltonian, actually acting at the map to the real line. And you could have the same, another type of flow, actually associated with the H3, and you will have until you get. I should use different color. Yeah, sorry. I should put different color. Yep. Okay. This is HN, right? Something like that. But everything that happening here is happening on the same thing here, on the side hypersurface. And this everything that happening on this hypersurface has to be consistent. What I mean by consistent is that there is this kind of thing happening, commuting map that I just mentioned to you before, right? This is complete the parallelogram here, commuting flow, commuting flow, right? You need that in order to make this whole thing, whole evolutions consistent, right? You need this kind of thing. Yeah. All right. I think that would be all for me to give you like a very introduction to the, I would say, Hamiltonian integrable system. I think there is, let me denote that if you want to read more, you can look on the textbook of the Babylon, an integrable system. That is the standard textbook on integrable system of the Babylon. or the textbook on classical mathematical. I'm not sure. I could not remember the title of the book, but the Arnold textbook on classical mechanics, I think maybe Arnold. That book is also, you can use that to understand this kind of whole thing. But for the Arnold book is a little bit difficult in terms of because he used the language of differential geometry a lot. It's a little bit abstract, I think. But well, it's not far from what I just gave you here, I believe. With this kind of basic, you can understand what he mentioned in that book, hopefully. And then what we have so far. So let me draw, let me give you a further possibility to read or interesting point. So normally in physics, so now you are on the Hamiltonian. What we have here is the Hamiltonian side, right? And then the key feature of this is the Hamiltonian commuting flow, right? Okay, but actually in physics, apart of the Hamiltonian function, you also can work with the Lagrangian, right? Lagrangian side, I would say. And same, this is the key feature for integrability. Right? On the Lagrangian side, there is also a key feature. It's called closure relation, which I haven't time to give you detail here. Closure relation here. This is also somehow in this kind of feature also somehow by integrability, right? This is kind of equivalent. This is in the same level somehow. So you can, if you are interested in this business, I mean, the Lagrangian point of view on how to define the notion of integrability, you can look at what I would say, Lagrangian multiform. This is the keyword. You can Google it, and you will see a lot of article on it. Lagrangian multiform, which is actually what they did, and it actually based on Weichenau principle. Okay, in order to get this closure relation, all right, and then they can show that actually the closure relation and the Hamiltonian commuting flow, they are equivalent. Okay, all right. I think actually there's something more like if you want to do with quantum stuff here, there is another big area of research here, and then it's not easy to deal with because in quantum your physical quantity to be the operators, and that there is the constraint about this kind of the operator that like commuting bracket somehow, and it's not easy at all to define the notion of the integrability in the quantum level. I think up to now there is no definite notion of integrability in the quantum level yet, because you may think that normally. So let me I still have time. Let me point out a little bit. So normally on the Hamiltonian side, So if you want to quantize, so you can go to Schrodinger wave equation, right? Something like that. You can put that, right? But well, you can do that. You need to solve this equation, right? Something like that. And for the Lagrangian side, you could do that by using Feynman picture or Feynman part integration, right? You compute the propagator, what you need, the propagator. Okay. But there is a problem on this side with this notion of the Liouville integrability, because you cannot you say that okay, let put this set of Hamiltonian, let's promote them to be the operator. Okay, and then there is there are some property that this set of operator have to satisfy, like quantum bracket commute, functional independent, something like the same thing that we do have in the classical level. But well, there is an encounter example that actually for non-integrable system can also possess that this kind of property as well. Then there is the naive way that you could you promote this Hamiltonian set to be the set of Hamiltonian operator. In this sense, is not kind of practical, applicable somehow, not that kind of practical. I would say applicable, because there is an encounter example that actually for non-integrable system can also possess this kind of structure as well. If you are interested, you can look on the paper on Stefan Weigert. He did show provide explicit example for that. Okay. And for this side, there is some recent development. The way that we looking for like integrability to the Feynman point of view, you can look at the work of King and Niehoff. I think it's very interesting work to look at. I do recommend you if you want to see how to quantize things through this Feynman point of view, and to define the notion of integrability in that way. All right, I think I shall stop here for my lecture, and hope you get more or less something today. If you don't, well, if you don't get the whole thing, that not surprised, because you might need time to digest. Well, I give you a huge bunch of things, then you might not familiar with, and you might need some time and to digest all of this thing. But at least I hope you get the point, all the main points that I communicate to you guys. All right, so I think I might probably stop here. Okay, I made very good time. And well, before I go, please don't forget to do the survey form for us, which actually will be provided in the, I think, in the Zoom link later after I stop the lecture. Let me say that the survey form, I think, going to be the Google form. There will be in English and also in Thai. For the foreigner, you go for the English, and for the Thai people, you go for the Thai version. And please complete the form for us, because every comment we're going to read, and then we're going to use it to improve our activity next time. Please do complete the form for us. And I think I'm going to stop now, and in the afternoon, the lectures will start at, I think, at 1 p.m. right? Is it right? Let me check for you as we still, well, let me. Okay. In the afternoon, the lecture will start at sharp 1 p.m. on the introduction to dark energy by Nandan Roy. Okay. So I think now it's time to break and have a good lunch for you guys. You can, I don't know, you probably could stay on the Zoom application, or let me find out that you should stay or you should go and then come back again. Well, it's actually nobody here in this room. It's only me. Okay. So, well, the one thing, if you have questions, please leave all the questions in the Slack channel or for this particular lecture. I'm going to look for that, for those all questions. I'm going to try to answer all of them later. Please. Or, well, if you have questions, you can turn on your microphone and ask me now, because we still have some, and then, well, nobody here. Let me. Okay. Okay, so I think you guys can, well, take a break now and go for lunch. I think you can leave the Zoom, I presume, and you can come back again in the afternoon. Let me find out this for you. So everyone, so you can stay on the Zoom though for the whole day. You can just physically leave for lunch and then you come back again, or you can leave the Zoom and log in again later in the afternoon. And for the survey form will be provided shortly after this. So all right, so thank you very much everyone for well, spare your time to listening to my lecture. Okay, thank you very much. Have a good lunch. Okay, thank you. Bye.